A pressure-independent control valve, often called a PICV, is a special type of valve used in modern heating and cooling systems. It's not just one simple valve. Think of it as three important parts combined into a single compact body. The first part is an automatic balancing valve, which helps control the water pressure. The second part is a differential pressure regulator, a key component that makes it pressure independent. The third part is a standard two-way control valve, which adjusts the flow of water. This clever combination allows the PICV to perform several jobs at once, making it a very useful device for engineers and technicians who design and maintain building comfort systems. The main job of a PICV is to deliver the correct amount of heated or chilled water to a terminal unit, such as a fan coil unit or an air handling unit. It does this regardless of how the pressure in the larger piping system changes. In a large building, many valves are opening and closing all the time. This causes the water pressure to go up and down constantly. A traditional control valve would let too much or too little water through when this happens. The PICV, however, has a built-in regulator that automatically adjusts to these pressure changes. This ensures that the flow rate you set is the flow rate you get, providing stable and predictable performance for the HVAC system. You can find PICVs installed in many different types of commercial and institutional buildings. They are commonly used on terminal units that provide heating or cooling to individual rooms or zones. These units include fan coil units, which are often found in hotel rooms and offices, and air handling units, which serve larger spaces like lobbies or entire floors. Chilled beams, another type of terminal unit, also benefit greatly from the precise flow control offered by a PICV. By using a PICV on each of these units, the entire hydronic system becomes easier to manage and more efficient, as each part of the system gets exactly the water it needs to operate correctly. In essence, the PICV simplifies the design and operation of a hydronic system. Instead of needing a separate balancing valve, a control valve, and sometimes other components, you only need one valve. This not only saves space, but also reduces the number of connections and potential leak points in the piping. The PICV is a smart valve that takes on the complex task of managing both flow and pressure. This allows the rest of the system, like the pumps and chillers, to work more effectively. It's really a fundamental building block for creating a high-performance, energy-efficient HVAC system in today's buildings, where comfort and cost savings are both very important goals to achieve. The importance of PICVs in modern HVAC systems cannot be overstated, especially when it comes to system balancing. Traditionally, balancing a hydronic system was a very time-consuming and difficult process. Technicians would have to go to every single valve in the building and manually adjust it. This process, known as static balancing, was often iterative, meaning that adjusting one valve would affect all the others. This required multiple passes through the entire building to get the flows just right. PICVs eliminate this entire process. Because each valve automatically regulates the flow to its terminal unit, the system is dynamically balanced from the moment it is turned on. This is a huge advantage for any new construction or renovation project. This automatic balancing feature leads directly to a significant reduction in commissioning time. Commissioning is the final step in a construction project where all systems are tested to make sure they work as designed. For HVAC systems, balancing is a major part of this process. With traditional valves, this could take weeks on a large project. With PICVs, the time needed for hydronic balancing is cut down dramatically. Technicians simply need to set the desired maximum flow rate on each PICV, and the valve takes care of the rest. This allows project teams to finish their work faster, reducing labor costs and allowing the building owner to occupy the space sooner, which is a major financial benefit. Another critical benefit of using PICVs is the improvement in energy efficiency. Traditional control valves often suffer from a problem called overflow. When system pressure increases, these valves allow more water to pass through the coil than is needed. This excess flow does not provide much extra heating or cooling but forces the pumps to work much harder, wasting a lot of electricity. Furthermore, this overflow of chilled water can lead to low delta T syndrome, where the water returning to the chiller is not warm enough. This makes the chiller operate very inefficiently. PICVs prevent this overflow by maintaining a constant flow, which helps the pumps and chillers operate at their most efficient points, saving significant energy over the life of the building. Ultimately, PICVs contribute to better overall building performance and occupant comfort. By delivering the precise amount of water needed, they ensure that each room or zone can maintain its set temperature accurately. There are no more complaints about some rooms being too hot while others are too cold. This stable operation also means less wear and tear on the major equipment like pumps, chillers, and boilers. Because the system is not constantly fighting against pressure fluctuations and overflow conditions, the equipment lasts longer and requires less maintenance. The combination of faster commissioning, energy savings, and improved comfort makes PICVs a standard and essential component in high-performance building design today. The working principle of a PICV is based on a clever mechanical design that combines two main functions into one valve body. The first function is performed by a differential pressure regulator. This regulator is essentially a diaphragm or piston connected to a spring. It constantly senses the pressure difference between the inlet and the outlet of the valve. The second function is performed by a control valve, which is usually a ball or globe-type valve. This part of the valve opens and closes to control the volume of water passing through. The key is that the control valve section is located after the differential pressure regulator has already done its job of stabilizing the pressure. Here is how it maintains a constant flow. Imagine the pressure in the main building pipe suddenly increases. This higher pressure pushes against the diaphragm inside the PICV's regulator section. The diaphragm moves against its spring and partially closes an internal passage, absorbing this extra pressure. As a result, the pressure reaching the control valve section remains steady and constant. The pressure difference across the control valve, the part that actually meters the flow, does not change, even though the main system pressure went up. Because the pressure drop across the control valve is constant, the flow rate will also remain constant, as long as the control valve position does not change. This is the pressure-independent feature in action. The role of the actuator is to control the amount of heating or cooling delivered to the space. The actuator is an electric motor that is mounted on top of the PICV. It receives a control signal from a thermostat or a building automation system. When the room needs more cooling, the thermostat sends a signal to the actuator, telling it to open the control valve section of the PICV further. This allows more chilled water to flow through the coil. When the room reaches the desired temperature, the signal tells the actuator to move the valve toward the closed position, reducing the flow. The actuator's job is simply to adjust the valve opening based on the thermal demand of the space. This is fundamentally different from how traditional control valves operate. A traditional two-way valve has no internal pressure regulator. Its flow rate is completely dependent on two things: its percentage of opening and the pressure difference across it. If the system pressure fluctuates, the flow through a traditional valve will also fluctuate, even if the actuator has not moved at all. This creates an unstable and inefficient system. A PICV, by separating the function of pressure regulation from the function of flow control, solves this problem entirely. The actuator controls the flow based on temperature needs, and the internal mechanics handle all the pressure variations automatically, ensuring stable and precise performance at all times. When you need to select a PICV for a specific application, there are two primary sizing parameters that you must consider carefully. The first and most important parameter is the design flow rate. This is the maximum amount of water, usually measured in gallons per minute or liters per second, that needs to pass through the valve to satisfy the heating or cooling load of the terminal unit at its peak design condition. This value is determined by the HVAC engineer during the system design phase. It's calculated based on the amount of heat the coil needs to transfer and the desired temperature difference of the water, the delta T. It's crucial to select a PICV that can accurately control this specific flow rate. The second key parameter is the operating differential pressure range of the valve. Every PICV is designed to work correctly only within a specific range of pressure differences between its inlet and outlet. This is often expressed in pounds per square inch or kilopascals. For example, a valve might be rated to operate between 5 psi and 50 psi. If the system pressure drop across the valve falls below the minimum requirement, say below 5 psi, the internal regulator cannot function properly, and the valve will no longer be pressure independent. It'll act like a simple orifice. If the pressure exceeds the maximum rating, it can cause noise, damage the valve, or prevent it from closing completely. Unlike traditional control valves, the valve size, like ½ inch or ¾ inch, is not the primary factor for selection. With old valves, you often had to pick an undersized valve to create enough pressure drop for good control authority. With PICVs, this is not necessary. You should select the valve based on the required flow rate, not the pipe size. Often, the correctly sized PICV will be smaller than the connecting pipe. For example, a terminal unit connected with 1-inch pipe might only require a 3/4 inch PICV to achieve the desired flow rate. Using a valve that is too large for the required flow will result in poor control, as small movements of the actuator will cause large changes in flow. Another factor to be aware of, though less critical for basic sizing, is the close-off pressure rating. This value tells you the maximum system pressure against which the valve's actuator can fully close the valve and hold it shut. This is important in high-pressure systems to ensure the valve can stop the flow completely when there is no call for heating or cooling. You must ensure that the pump head in the system does not exceed the close-off pressure rating of the selected valve and actuator combination. Checking these parameters, design flow rate, differential pressure range, and close-off pressure, will ensure you choose the right PICV for reliable and efficient operation. Alright, let's walk through a simple example of how to size a pressure independent control valve, or PICV, for a small fan coil unit. First, the HVAC engineer has calculated that the fan coil needs a maximum of 4.5 gallons per minute of chilled water to provide enough cooling on the hottest day. This is our design flow rate. Next, the engineer has also figured out that the differential pressure available at the location of the valve will vary between 10 and 35 pounds per square inch as other valves in the system open and close. So, this is our operating differential pressure range. Our goal here is to find a PICV that can deliver 4.5 gallons per minute and works properly within this 10 to 35 psi range. Now we need to look at a manufacturer's selection chart or table. These charts are usually found in the technical data sheets for the PICVs. The chart will typically list different valve models, often organized by their connection size, like half-inch or three-quarter inch. For each model, it'll show a range of adjustable maximum flow rates. What we need to do is find a valve model where our target flow rate of 4.5 gallons per minute falls comfortably within its adjustment range. For instance, let's say we find a 3/4 inch valve model that has an adjustable flow range from 2 to 5.5 gallons per minute. That would be a good candidate because our 4.5 gallon per minute target is well within this range, not sitting right at the extreme high or low end. After you've found a valve with the correct flow rate range, you also need to check its required operating differential pressure. The manufacturer's datasheet will specify the minimum and maximum pressure drop the valve needs to function. For example, the 3/4 inch valve we found might require a minimum of 5 psi to operate and have a maximum rating of 60 psi. Our system's pressure range is 10 to 35 psi. Since this range is entirely within the valve's acceptable limits of 5 to 60 psi, this valve is an excellent choice. But if our system pressure could drop to, say, 3 psi, this valve wouldn't work correctly and we'd need to find a different model with a lower minimum pressure requirement. Once the correct valve model is identified, the final step during installation is to set the maximum flow rate on the valve itself. Most PICVs have a dial or a screw adjustment that can be set to the desired maximum gallons per minute. In our example, the technician would adjust the dial on the 3/4 inch valve to the 4.5 gallons per minute mark. Once set, the valve will never allow more than 4.5 gallons per minute to pass through it, no matter how high the system pressure gets, as long as it's within the operating range. The actuator will then modulate the flow between 0 and 4.5 gallons per minute to control the room temperature. This simple process of checking flow rate and pressure ensures accurate and efficient system performance. Proper installation is, honestly, crucial for a PICV to perform as intended. One of the most important considerations is the valve's placement in the piping. The PICV should always be installed on the return pipe coming out of the heating or cooling coil. Placing it on the return side helps protect the valve's internal diaphragm from the extreme temperatures of the supply water, which can really prolong its life. Additionally, it's essential to install the valve with the arrow on the valve body pointing in the direction of the water flow. Installing it backward will prevent the valve from working correctly and could even cause damage to its internal components. This is a simple but, very important step to follow. Another key installation tip is to ensure there is a sufficient length of straight pipe before the valve inlet. Most manufacturers recommend a straight pipe length of at least 5 to 10 pipe diameters upstream of the PICV. This is because turbulence in the water flow, caused by elbows, T's, or other fittings, can interfere with the valve's ability to accurately sense pressure and regulate flow. Providing a smooth, straight path for the water entering the valve allows it to operate with maximum precision and stability. While some modern PICV designs are less sensitive to turbulence, following this guideline is always a good practice to ensure optimal performance of the entire system. When installing the valve, it's also important to think about future service and maintenance. Always install isolation valves, which are just simple shut-off valves, both upstream and downstream of the PICV. These isolation valves allow a technician to completely shut off water flow to the PICV without having to drain the entire piping system. This makes it much easier to replace the actuator or service the valve if needed. Additionally, a strainer should be installed upstream of the PICV to catch any dirt, rust, or debris from the pipes. This protects the delicate internal parts of the PICV from getting clogged or damaged, which is honestly a common cause of valve failure. Finally, you must leave adequate physical space for the actuator and for future access. The actuator is mounted on top of the valve and requires clearance above it so it can be easily installed or removed. Technicians also need physical space around the valve to get their hands and tools in to make adjustments to the flow setting dial or to perform service. Sometimes valves are installed in tight ceiling spaces or behind access panels. It's the installer's responsibility to ensure the PICV is positioned in a way that allows for easy access later on. Planning for this during the initial installation will save a lot of time and frustration during future maintenance activities. One of the most common mistakes made with PICVs is incorrect sizing. This often happens when engineers or contractors are used to sizing traditional control valves. They might select a PICV that is the same size as the connecting pipe, such as a 1-inch valve for a 1-inch pipe, without checking the required flow rate. This frequently results in a valve that is far too large for the application. An oversized PICV will have very poor control characteristics. The slightest movement of the actuator will cause a large change in flow, leading to the system hunting for the set point and unstable temperature control. Always size the valve based on the design flow rate, not the pipe size. Another frequent error is ignoring the minimum differential pressure requirement of the valve. Every PICV needs a certain minimum pressure drop across it to power its internal pressure regulating mechanism. If a valve is placed at the end of a long pipe run where the pressure is very low, it might not meet this minimum threshold. When this happens, the valve loses its pressure independence and behaves like a simple fixed orifice. It will no longer be able to control flow accurately, and the terminal unit it serves will likely be starved of water, leading to a lack of heating or cooling. It's critical to perform a hydraulic calculation to ensure enough pressure is available at every valve location. A surprisingly common installation mistake is mounting the valve backward. All PICVs have an arrow cast or stamped onto the valve body to indicate the correct direction of water flow. If the valve is installed with the arrow pointing against the flow, it simply will not work. The internal diaphragm and spring are designed to work with pressure on one specific side. Reversing the flow can force the valve shut or cause it to remain wide open, and it will certainly not regulate pressure. This simple mistake can cause major headaches during system startup and requires costly rework to cut the pipe and reinstall the valve correctly. Always double-check the flow arrow before welding or threading the valve into place. Finally, a mistake that undermines the entire purpose of a PICV is installing a separate manual balancing valve in series with it. Some designers or installers, out of habit from working with older systems, might add a balancing valve just in case. This is completely unnecessary and counterproductive. The PICV is an automatic balancing valve itself. Adding a manual valve just adds extra cost and creates an additional source of pressure drop in the system. This can potentially starve the PICV of the pressure it needs to operate correctly. Trust the PICV to do its job. The design should be simplified to include only the PICV isolation valves and a strainer. Integrating PICVs with a building automation system, or BAS, is a straightforward process that really unlocks their full potential for energy efficiency and smart control. The PICV's actuator is the key component for this integration. Most modern actuators are designed to accept standard analog control signals from a BS controller. The most common signal types are 0 to 10 volts DC or 4 to 20 milliamps. In a typical setup, the BS sends a signal to the actuator, where 0 volts, or 4 milliamps, corresponds to the valve being fully closed, and 10 volts, or 20 milliamps, corresponds to the valve being fully open to its preset maximum flow rate. This allows for precise, proportional control. The BAS uses this control signal to modulate the valve's position based on real-time data from the building. For example, a temperature sensor in a room feeds data to the BAS controller. The controller compares the actual room temperature to the desired set point. If the room is too warm, the BAS will increase the voltage signal to the PICV actuator, causing the valve to open more and allow more chilled water to flow. As the room cools down and approaches the set point, the BAS will gradually decrease the signal, closing the valve. This continuous adjustment ensures that just the right amount of energy is used to maintain occupant comfort, without the waste associated with on-off control. A significant maintenance benefit of this integration is the ability of the BAS to provide feedback from the valve. Many advanced actuators can send a feedback signal back to the BAS, indicating the actual position of the valve. This is extremely useful for troubleshooting. For instance, if the BAS is sending a 10-volt signal to open a valve, but a flow meter in the system shows no water is flowing, the BAS can check the valve's position feedback. If the feedback shows the valve is closed, it could indicate a failed actuator or a wiring problem. This allows maintenance staff to diagnose issues remotely from a central computer instead of having to physically inspect every valve in the building. Furthermore, integrating PICVs with a BAS enables advanced control strategies that lead to greater system-wide energy savings. For example, the BAS can monitor the demand from all the PICVs in the building. If it sees that most valves are only partially open, it knows that the building's cooling load is low. The BAS can then send a signal to the variable speed pumps to slow them down, reducing pumping energy. This is known as demand-based pressure reset control. This holistic control is only possible because the PICVs ensure that each terminal unit receives stable flow, allowing the central plant to adjust its output confidently to match the building's actual real-time demand. To recap, the benefits of using pressure-independent control valves are substantial and impact nearly every aspect of an HVAC system's life cycle, from design to long-term operation. The most immediate benefit is the dramatic energy savings achieved. By preventing overflow at the cooling coils, PICVs ensure an optimal temperature difference, or delta T. This allows chillers and boilers to run at their peak efficiency. Additionally, by providing stable flow, they enable variable speed pumps to slow down and match the true load of the building, which is one of the single largest sources of energy savings in modern hydronic systems. These savings continue year after year, significantly reducing the building's operating costs. Another lasting benefit is the superior comfort provided to the building's occupants. Unstable flow in traditional systems often leads to temperature swings, with rooms becoming too hot or too cold. This problem, often called hunting, is a common source of complaints. PICVs eliminate this issue by delivering a precise and steady flow of water to each terminal unit, regardless of pressure changes elsewhere in the system. This results in stable and accurate temperature control in every zone. A comfortable environment leads to happier and more productive occupants, whether they are office workers, hotel guests, or hospital patients, adding significant value to the property. From a maintenance perspective, PICVs offer a clear advantage by reducing the burden on facility staff. The dynamic balancing feature means that the system rarely needs to be rebalanced after the initial setup. This saves countless hours of labor over the life of the building. Furthermore, by ensuring the system operates under stable conditions, PICVs reduce wear and tear on expensive equipment like pumps, chillers, and actuators. Fewer equipment breakdowns and less need for troubleshooting mean lower maintenance budgets and a more reliable HVAC system. The system simply works better and requires less intervention from the maintenance team. In conclusion, the decision to use PICVs is an investment in a simpler, more efficient, and more reliable HVAC system. They simplify the initial design by combining 3 valves into one. They slash commissioning time by eliminating the need for manual balancing. They deliver significant ongoing energy savings by optimizing the performance of the entire hydronic plant. They improve occupant comfort by providing stable temperature control. And finally, they reduce the long-term maintenance effort required to keep the system running smoothly. For all these reasons, the pressure-independent control valve has become a standard and indispensable component in modern high-performance buildings.